But mankind won't be destroyed. The fact that you and I are working here today is evidence of that.
Ignition. Liftoff.
While we are all joining this event from our own location, we would like to acknowledge that we are meeting on the lands of the Wurundjeri people and the Boon Wurrung people of the Southeast Kulin Nation. We would like to pay our respects to their elders, past, present and emerging, and to all First Nations communities joining us today. Welcome everyone, either from Australia or overseas, to another night at the Observatory. Tonight's 7.1 stream is all about telescopes. I'd like to begin the segment by introducing you all to our panelists who will be presenting this evening. Could you please join me, Merv, Drew, Jamie, Stuart, Jeff, Adam, Andrew, and of course myself, Petra, who will be your host for this evening. And before we begin, I'd like to give a shout out, as always, to our fabulous crew who are working hard behind the scenes and on Facebook and YouTube tonight. They too play a big part in bringing this production to you. So we at Mbo have noticed that throughout all our live streams, you, the public, have always asked questions regarding telescopes. So our team have decided to bring to you a stream dedicated to them. Bear in mind that this is a broad and expansive concept, and we can't cover the entire topic or answer all of your questions in one session. This is just a primer, somewhere to get you started, and you may need to do your own research regarding telescopes, or you could come and join us and come up to Mbo. Remember, telescopes are a 400+ year invention, and there's been a lot of development done on them. And we can't summarize that, including the entire current market, in 1 hour. However, Mbo is great for helping people decide which telescopes are good for them, and believe it or not, that is how some members have ended up joining us. So let's get started. And first up for tonight's show, we have Merv, who will be presenting, or should I say, constructing telescopes.
Hi, I thought I'd introduce you to Astral Arts and maybe a couple of things what I'm doing, but what is Astral Arts? Well, it's being creative with astronomy, displaying images like Neil does up at the Mbo, modifying photographs and make the stars really pop, transfer an image to a t-shirt, paint a starscape. Van Gogh did that many years ago. Some people have copied it. There's poetry and song. Starry, starry night, need I say more? You could do a 3D print if you've got a 3D printer, or create a sculpture. Then again, you could do what I did. Build your own telescope or replica of Galileo. I'll give you a little bit more information about these later. And another project here is making a Hubble telescope. So it's only part finished. And again, I'll give you a few more hints and clues what you can do. Okay, have fun. It's not so difficult to make a Galileo telescope. You need some tubing, an objective lens, and an eyepiece. Okay, your tubing, you can get that from a local material store. Cut off what you need. So you have a piece of tubing. You may need to cut something to go inside that and help stack it out a little bit. But now you can take a lens, pop it inside. And again, you can cut this off to suit yourself. Get some tubing that's extendable. Things like from your Glad wrap or kitchen roll paper. So some tubing that can slide, and you can basically create a telescope. So here we have it. Your eyepiece for the end here can maybe come from an old pair of binoculars I've got. Just a few bits and bobs. So, the basics of a telescope. Once you've got your tubing done, you can cover it. Get some cloth from a local op shop maybe, an old dress or jacket or something with leather, different colours. Pretty it up a bit, some different colours as well. And when you're finished, you can do some decoration. So, get in there, and what have we got? A little bit of this. Get some thinner ones. As well, you can make your own design or copy what Galileo did originally. Entirely up to you. Have fun. Make your own telescope. So, what's needed to make a model of a Hubble telescope? Now, my model here, I've already built the interior, complete with its mirror, primary mirror, and secondary mirror in here. I'm in the process of building the exterior, and this is my first attempt, which is pretty plain because it's on white paper or white card. My second attempt, I used some silver card. There is issues with this, but it looks a little better, I think. And the printed sheets, there's about 15 sheets like this, and this, and this, and so on. Some of them you need to put on heavy cardboard backing. You can either use stiff card or maybe a cereal packet. Once you've got your sheets, you start carefully cutting them out and shaping them and gluing them. So, putting the sheets aside for a moment, just keep this one here. Some of the tools you'll need, of course, is a cutting board, a rule, a cutting knife. Remember to count your fingers before you start and afterwards. And for cutting circular bits, you might want one of these devices where you can cut circles carefully. Remember, cut the outside circle before you cut the inside circle, otherwise you'll be cutting out your center point. Scissors, some elastic bands to hold things together as you've glued them. Of course, you need some glues, maybe a little bit of super glue. Tweezers to hold the finer components, your pencil to mark some of the items, and again, maybe some of these little crocodile clips to hold finer items. The glue, again, I used the bottle to help wrap some of the shapes around, like when I was rolling this into a circle, so I was using that to help roll the paper. And get yourself a couple of little canisters to hold the small bits and pieces. So in here, I've got, I don't know if you can see that or not, but it's one of the tiny little boxes, and some other what they call scuff plates. So keep yourself a box for holding the small parts, and hopefully have some fun. Now, if you're really interested in doing this, let me know, and I'll share the web link and also give you some hints and tips about the pitfalls of making a Hubble telescope. Have fun. Cheers.
NASA made history this week with the first ever flight of an aircraft on another planet. The Ingenuity helicopter, which travelled to Mars with the Perseverance rover, flew for about 10 seconds to a height of 3 meters. This initial test has since been followed by 2 longer, higher flights. This is primarily a technology pathfinder for future Mars flight missions, but Ingenuity will help the Perseverance mission by scouting ahead of its path and providing a different perspective on Mars. Mount Bennett Observatory is a community-run astronomical society in the Dandenong Ranges. We are completely volunteer run and have over 500 members. We focus on community engagement, outreach, diversity, and helping our members to get the most out of their love of space and astronomy. The observatory was originally built by Monash University for students to do astronomical research, especially on variable stars, stars whose brightness changes over time. Over the next 2 decades, the site was expanded and upgraded, but eventually took a back seat to modern giant internet-connected observatories around the world. In 2011, our 5 founding members reached an agreement with the landowners and took over the lease and established a society. Now, we run over 80 events each year, including members' nights, public viewings, and special events. We have several special interest groups including deep sky observing, radio astronomy, astrophotography, Astral Arts, and young observers. In 2020, we expanded our online presence and now host regular live streaming events. We welcome all new members and love making new friends with other astronomy lovers. You will be joining a friendly community of passionate, hard-working amateurs who have a grand vision for the future of the observatory. We hope to see you up at Mbo soon.
Our next presenter will be Drew. Drew has some interesting facts to share.
Thank you, Petra. I'd just like to take a break from talking about telescopes for a moment and talk a little bit about Now, previously we've seen how the Earth is tilted at an angle of 23.5 degrees relative to our orbit around the Sun. So the Earth's axis there, which is visible in white, instead of pointing straight up and down, it's at 23.5 degrees angle. I've also previously talked about the equator, which runs around the middle of the Earth, and I've drawn it in green there. And just as the axis is tilted at 23.5 degrees, so too is the equator, because the whole Earth is. But tonight I'm going to introduce another imaginary line, the ecliptic. The ecliptic goes around the middle like the equator does, but the ecliptic goes around in the line with the Sun, so it basically follows the path the Sun appears to take around us, or to be more precise, it's in line with the path we take around the Sun. Now, that's great, you say. It's another term to memorize, but it doesn't sound overly useful. Well, I'll talk a little bit about that. Just show you this diagram here, nice diagram of the solar system. And we can see all the planets there. They're slightly out of scale. If this was to scale, some of the planets would be in some of your land rooms, and so it wouldn't be very practical. But what this diagram does show is everything is basically in one flat plane. All the things go around the Sun the same way. That's quite important. Coming back to what I was showing you before, we have the ecliptic there, and the Sun appears to travel around along the ecliptic line. But given that everything in all the planets in the solar system, at least, not Pluto or the other dwarf planets, given that all the planets and their moons travel around in one flat plane, they basically all follow the ecliptic as well. So as well as the Sun in one direction, we've got Mercury and Venus. And when we look outwards, we've got all the other planets and moons, Jupiter, Saturn, and so forth. And they all travel in that same plane, or as I've drawn it here, horizontally. So all of the main objects in the solar system travel along this neat path, and that's why the Mercury and Venus and Saturn might all be lined up in a row one evening. That's not a coincidence. That's the way everything, including the Earth, moves through the solar system. Now, along the ecliptic, there are 13 constellations. We have, not in order, but in alphabetical order, we have Aquarius, Aries, Cancer, Capricornus, Gemini, Leo, Libra, Ophiuchus, Pisces, Sagittarius, Scorpius, Taurus, and Virgo. And that should be 13 if I've counted correctly. Now, they're all astronomical constellations, and they go around, as I've said, the ecliptic. Now, of those 13, the Babylonians saw them and decided to use them in astrology, and 12 of the 13 became zodiac houses, where all the planets and the sun conveniently move through. So we have Aquarius, which is based on the constellation Aquarius, Aries, based on Aries, the ram, Cancer, based on Cancer, Capricorn, based on Capricornus, maybe they lost a syllable along the way or something. Gemini is Gemini, Leo is Leo, Libra is Libra, Ophiuchus, well, I'll talk a little bit more about that in a moment. Pisces is Pisces, Sagittarius is Sagittarius, Scorpio is Scorpius, Taurus is Taurus, and Virgo is Virgo. Now, before I talk a little bit more about those, there's something I need to point out when I talk about astrology here. Astrology is not astronomy. Astronomy is a science where we're constantly modeling the universe and making theories about them and then testing those theories, throwing away the ones that don't work and coming up with new ones to explain the universe better. Astrology is not. Astrology is the planets are here, so we're going to predict this happens. It's very important, especially when talking to an astronomer, not to confuse the two. Anyway, as I've said, 12 of the 13 became zodiac houses in astrology. Why did this happen? Well, the Babylonians who came up with the zodiac decided 12 was a better number to work with. 13's a little bit odd. So they had to leave one out, and they left out Ophiuchus. Now, it is not going to become a new star sign. From time to time, and I've seen it recently, news articles, and I use that term advisedly, come out saying, there's this new star sign, Ophiuchus. It's some new revelation, or because of Ophiuchus, astronomers have decided to rearrange the star signs and they're all going to change on you. No, astronomers do not do that. There are 13 constellations around the ecliptic, but there are only 12 star signs, and although one is based on the other, none of this is going to happen, so don't worry about it. If you see any of those news articles, just have a laugh and move on to the next page. There's probably something more important there. Anyway, we have meteor showers that happen regularly. As we move along the line of the ecliptic around the sun, or as the sun and other planets appear to move around the ecliptic around us, we go through meteor showers. Meteor showers appear to come from constellations, and they're named based on that. But it's actually the path of the Earth moving through debris that causes meteor showers. Now, because we're moving along the ecliptic, a lot of the constellations around the ecliptic are going to appear to be the source of showers. And here I've got a nice little diagram of a meteor shower or two. And next to it, I've got some of the names of some of the meteor showers. Some of these names, if you look closely at them, might be slightly familiar. We've got Aquarids that come from Aquarius, Leonus from Leo, Taurids from Taurus, Ophiuchids from Ophiuchus, Capricornids from Capricorn, Geminids from Gemini, and so forth. Anyway, I'll close up here and just summarize. The equator that we've talked about previously is a line of division between the northern and southern hemispheres, which is aligned with the Earth's axis at an angle of 23.5 degrees. The ecliptic is a similar line, aligned with the angle of the solar system, and hence it's where everything appears to travel. So that's the end of my presentation. Now let's get back to some telescope stuff.
Thanks for that, Drew. And yes, people, please do not confuse astronomy with astrology. But if you do want to see the constellations with a telescope, remember they are along the ecliptic. Now, I must also thank Merv for his earlier presentation because he had some really great projects, something that the whole family can do together. Now, our next presenter we have is Jamie, and she will be informing us about telescopes in space.
All right, thanks, Petra. So we all know that we've got such things as satellites. Now we've got satellites that are actually telescopes. Now you might recognize one of those images on the screen there as the Hubble Space Telescope. So we're going to start with that one there, by NASA and the European Space Agency, or the ESA, back in 1990, and it's in a low Earth orbit around the Earth, and it uses visible, ultraviolet, and near-infrared spectrums to take some of these beautiful images that I'm sure you've all seen at some point in your life. This example on the screen there is of the Horsehead Nebula, is one that Hubble took a little while ago. And back in 2009, it was anticipated to only last another 5 years. Now it is 2021 and it is still going, and hopefully it'll be around until the James Webb Telescope is launched in October this year. So keep an eye out for that one. And it primarily targets deep space objects. Now, Hubble also has what is called the Hubble Ultra Deep Field, which is this photo that you can see here. And every spot of light that you can see on the screen there is actually a galaxy, with the exception of ones that have got little spokes of light coming off them. They are stars that are within our galaxy, but all of the rest of it is all galaxies. Have a think about that. How small must we be compared to all of it? Just got a little video there to show you as well, if our tech support team can handle that one, of the Hubble launch.
And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope. Our window on the universe.
All right, thank you, tech support. So that sums up the little bit of information I've got there for you for Hubble. If you want to know a bit more about any of these telescopes in the presentation, to have a look on NASA for more. So moving on, another one is the Kepler Space Telescope. Now, this one was launched back in 2009, once again by NASA, and this one is in a bit of a different orbit than the Hubble Space Telescope. It's in what is called a heliocentric orbit. So it orbits the barycenter of the sun, which is within or near the sun's surface. And as it goes around the sun, it actually falls further and further behind Earth, which I'll show you a little bit more on in just a second. Now, Kepler uses the visible light spectrum to obtain the images that it sends back to Earth. And the first images came back to Earth on April 16 of 2009. And it started to search for extrasolar or exoplanets back in May of 2009. This was its main mission before it was decommissioned back in 2018. So you can see there's just a bit of a graphic of how Kepler orbits the sun. So it's following behind Earth fairly closely there, but as it progresses, it falls further and further behind. So if you watch it for a little bit, you'll notice that the gap in between the Earth and the telescope is getting increasingly larger. This is from NASA as well. Now, the next one we've got is Galax, is another NASA mission, was launched back in 2003, is in a low Earth orbit, so similar to the Hubble, which we talked about before. And this one uses ultraviolet light to find galaxies. So it's mainly focusing on their shape and their size and how far away they are from us. This one was decommissioned back in 2013, and you can see there some of the beautiful images of some of the many galaxies that we've got in our universe with us as well. The different colors just represent different gases that are within the galaxies. So you've got things like hydrogen and helium that show up as different colors on the spectrum, and that's what the different light waves tell us. So we use those for various different things. So the next one is the Solar and Heliospheric Observatory, or Soho, which was launched by NASA back in 1995. And this one uses optical to ultraviolet light and magnetic imaging. And you can see there's a moving image on the bottom right-hand side there is an example of some of the things that Soho is looking at. This one is in what's called a halo orbit, which I'll show you in just a second as well. But what this means is that Soho has an uninterrupted view of the sun. So there's no interference from any eclipses from its perspective between the Earth and the sun. So since its launch, it's taken images of the sun's convection zone, the structure of sunspots beneath the surface of the sun itself, and it's discovered different phenomena as well, such as solar tornadoes. So that moving image down there on the right-hand side is an example of one of those. Contrary to its name, it's not actually a tornado. It is just an emission of mass from the sun. So this is an image of how Soho orbits. So it follows around Earth, but it moves around in one spot. So up on the right-hand side there is looking towards the sun. We've got Earth in the left-hand corner there. And Soho kind of sits in between them, about 1.5 million kilometers away from the sun, and moves around in a circle to get different angles to observe the sun. And last but not least, we've got Stereo, was launched by NASA back in 2006 and uses visible, ultraviolet and radio wavelengths to capture images of the sun. This one's actually two crafts. We've got Stereo A and Stereo B, and the image on the top left there just shows how they orbit around the sun. So you've got both of them are kind of at opposite points of the sun there. And these are in the same sort of orbit as Kepler, so following behind Earth, a heliocentric orbit again. And this one focuses on taking images of coronal mass ejections, or CMEs. These can impact us down here on Earth as well. They can interrupt satellite communications and GPS and phone lines and all sorts of things. So they're not exactly good news, but we do have the Earth's atmosphere to protect us from the worst of that. So it's okay. Don't lose any sleep over it. We'll be fine. Now, we lost contact with Stereo B back in 2016, but Stereo A is still out there and still operational. And that does it for my presentation. Hope you enjoyed. Back to you, Petra.
Thanks, Jamie. There were some telescopes that you spoke about that I didn't even know had made it into space. Before we head into a news break, I'd like to say, don't forget, if you have any questions about tonight, drop them into the comments and we'll attempt to answer them. There is also a planisphere giveaway for the question of the night. And now for our news break.
Under construction for several years, the new space telescope, the James Webb, is nearly ready for its planned launch in October of this year. This month, the huge sunshade that will help keep the telescope cool from the sun was folded in a significant part of the process required to get it to fit in the fairing of the Ariane 5 rocket, which will take it into space. Once launched and operational, the James Webb will provide a new view of the universe, including the oldest galaxies and the atmospheres of exoplanets.
Next up, we have Stuart. He's going to share some physics with us.
Hello, everyone. I thought when I heard we were going to talk about telescopes, I thought, why don't I pick the most interesting sounding word I can think of? And so I'm talking about interferometry. So interferometry is a word that describes a lot of different measurement techniques that cross a large number of scientific fields. They all have to do with measuring precise measurements using wave properties. But I'll specifically be talking about how interferometry is applied to telescopes. And so yeah, we'll get to the wave properties a bit later, but first the basics of relevant areas of telescopes. Telescopes come in lots of different shapes and sizes, and they have all got different things going on inside of them, and complex focusing and processing and all that. But what really matters, well, they're incredibly complicated in some cases because they've had centuries to be refined and all that. And if you're looking to buy a telescope, you should care about some of these finer details. And for that, I'd encourage you to inquire with other members of our team or other people knowledgeable about such telescope-y things. But it's unmistakable that one of the important things of telescopes is the aperture. The aperture is a fancy name for the light collecting area of a telescope. Though if you hear a number given to an aperture, it's usually the diameter of the primary optical element, usually the mirror or lens. So yeah, you can see it for those telescopes given there. So yeah, the aperture is very helpful. When looking through an amateur telescope, the first limit to what you can actually see with a telescope that you'd probably come up against is brightness. You can't see dim things, and it turns out if you have a larger telescope with a larger aperture, to be specific, you can see dimmer objects because with a larger aperture you can collect more light, and that's the goal of any telescope. Professional telescopes can actually push past this limit, and that the limit of having a very dim object is actually very fuzzy. It's not a hard limit because with professional telescopes they can put a camera instead of an eye up to a telescope. Now the human eye, it kind of resets its light sensors very rapidly so that we can see motion, so that yeah, we can watch those 60 frame per second movies and all of that. But that doesn't help for looking up into space. You want to, so for cameras and other sensors, they like to keep them looking at space for a very long time, and then it's just a matter of time before you collect enough light to be able to see very dim objects. So the professional astronomers don't have to have a large aperture to see very dim objects. They just have to look a very long time. But that, of course, has its own practical limitations because eventually another astronomer is going to come along and say, hey, it's my turn on the telescope. Don't make me call your mum. Yes, professional astronomers live very cutthroat lives. But of course, this can also be helped by having a larger aperture, because having a larger aperture means that you collect more light, means that it takes less time to collect enough light to see something. So yeah, we've refined telescopes for centuries now, and scientists have come across another limit to what we can see. This is the diffraction limit. You probably won't come across this in an amateur telescope. You need very precise measurements to get rid of all of the other things that interrupt your viewing. But if you have two objects that are closer together than the diffraction limit of your telescope, then they end up blurring together, and you won't be able to see them as separate objects. So the diffraction limit stops you seeing objects that are smaller or further away than your telescope allows. Yeah, so this is a fundamental property of light, specifically to do with waves. So you can't fix this with focusing or processing after you've collected all the light. So it's a inherently wave mechanic of light that produces the diffraction pattern. And I'll just go through a bit of theory here. Here we've got two waves of light, and they're all lined up. They're in phase, as they say. And if they met together, then the high points would add to the high points, the low points would add to the low points, and you'd end up with a very strong signal. This is constructive interference. Likewise, you can have waves that meet completely out of phase, as they say, and here the high and low points cancel out, then you end up with no signal. The wave disappears, and that's destructive interference. And yeah, if you've noticed the word interference, then you might be able to guess where the name interferometry comes from. So how does this all effect come into practice with telescopes? Yeah, so here we've got a very simple telescope. It's got a big mirror at the bottom here, primary element, and the box up here represents a camera or sensor that you see through. So if we're looking at a star that's right above us, then it's going to send waves of light down to the telescope. I've got the dot and dash pattern for this light ray to represent a wave. It's got low parts and high parts. And you'll notice that for this specific example, it's completely symmetric. What I want you to take note of is that it's the exact same distance that these two light rays have to travel to get to the light sensor. And that means they meet at the same phase and they constructively interfere to give us a signal. That's a very complicated way to say this telescope can see that star. But now we're looking at a star that's slightly off at an angle. Here's the light coming from that star. And this situation is not symmetric. And one of the light rays has to travel a further distance to get to the light sensor. This means that there's a slight difference in the phase of the light. Though specifically in this situation, if you can see the details, it's not completely out of phase. We're still going to get a signal from this. And because it's still on the light section of both light rays when they hit the sensor. And so that means that this star that we're looking at is within the diffraction limit of the other star that we were looking at for this very crude diagram I have here. So how can we differentiate these two stars in an image? Like I've been training you to know the answer to, you get a bigger aperture of your telescope. With a bigger aperture, there's a bigger difference in the distance that the light has to travel for these two light rays. And in the middle, they now meet out of phase. They destructively interfere. So we can no longer pick up a signal at that specific point on the sensor from that star. So that means we can differentiate them. But the next pixel over on the camera might be able to have a constructive interference and see that other star with a slightly different geometry. Well done for anyone who followed what I was saying there. That was the complex physics side of interferometry. The important thing I want you to take away is that the information that allows you to see finer and smaller details in something, we get that information from the outside portion of the dish, where the difference in phase of the light is the largest. So yeah, what's on the slide, that's not always important. You don't have to worry too much about that. What was I talking about? That's right, apertures. You always need a bigger aperture. So throw away all those common commercially available telescopes. At MBO, we've got a telescope that has an aperture of nearly 0.5 meter. Wowee, that's impressive. Imagine a club having a telescope that large. How incredible, what incredible things could you see with that? Don't you just want to join a club that has such an incredible instrument? But anyway, eventually you might think, is there a bigger telescope than this? And of course there is. The largest optical telescope in the world is in Spain, and it's around 10 meters in diameter. That's simply enormous. But it doesn't stop there. We can always have a larger aperture. If you weren't aware, radio waves, they're a form of light, and so they behave the exact same way, in enough. And so they behave the same as optical light, but they're a lot less picky about what they reflect off. So instead of grinding out a really smooth mirror, we can just kind of put a metal frame together, and that's enough to reflect radio waves. So now we can make radio telescopes, and they're cheaper and easier to make larger versions of. So here's the Australian Parkes Radio Observatory telescope that's 64 meters away, the famous dish. But of course, we can get bigger. Here is a picture of the Arecibo telescope. are 305 meters across, truly enormous. But RIP, it is no longer in working operation and has collapsed. A moment of silence, please. But of course, we can get larger. Don't wait too long. We've got a 500-meter wide telescope in China, and that's the largest telescopic dish on the planet. Wowie. The fast name of this telescope is actually an acronym for 500-meter Aperture Spherical Telescope. Don't say that astronomers are bad at naming things. But honestly, 500 meters, I think I speak for everyone when I say it's a bit small. We could go bigger. And so why don't we go and make a telescope the size of the world? And when I say this to other astronomers, they're all like, no one's going to pay for that. It's structurally impossible. There's not even a theoretical material that could support its weight. There's not enough material in the crust of the Earth in order to construct it. Silly concerns like that. But I want my telescope because you can never have an aperture that's too big. And here's where interferometry comes into play. So what allows us to, the big advantage of having a large aperture for professional astronomers is to get out that those finer details. And that requires you to have a large dish because it can tell the difference, the large difference between the phase of the light at these two ends. Someone had the smart idea of splitting a possibly large telescope into smaller telescopes and then smushing the light together afterwards. Of course, the process of this requires you to know the exact phase of light. So it's not a amateur telescope job to use interferometry. It requires very precise measurements. In optical interferometry telescopes and other telescopes, the methods they use require them to have a big channel between the telescopes that they precisely shoot the light down to put it together later and figure out the phase difference. For larger wavelengths, like radio telescopes, they can measure the light. We have the technology to measure the exact phase of the light. And now that we have atomic clocks, we can sync those telescopes up no matter how far away they are from each other. Interferometry is actually very common in radio astronomy for this reason of ease. And so usually if you see a bunch of telescopic radio telescope dishes, you'll usually find them in an array. And that's the reason, because we like to combine them together to make a effectively larger telescope. But now that we can separate them arbitrarily, can my dream of a telescope as large as the Earth come to fruition? And the answer is yes. It's more than a dream. It's a reality. Someone's already done it. The Event Horizon Telescope is not actually a telescope as we would think, but it's a collaboration between telescopes across the world, and abusing the fact that all the telescopes are really far away from each other, and also abusing the fact that the Earth is rotating to help fill out, color in the giant dish that we're making. They've been able to make a telescope that, in terms of the diffraction limit of that telescope, acts like it has an aperture of the entire planet. And one of the most notable images that they've been able to take in this initiative is the one here, the picture of the supermassive black hole at the center of M87. And that image might look a bit blurry, but it's actually one of the images that has the highest resolution ever taken by humanity. So don't think too smallly of it. It's also the first image that we have of a black hole. So interferometry solves all of our structural problems. Now we can have an aperture as large as we want. We could just send a few probes out and have one as large as the solar system. And after that, why not have one as large as a galaxy? And why stop there? The observable universe, we could have a telescope as large as everything there is. You can never have a telescope that has an aperture that is too big. Thank you.
Thanks for that information, Stuart. We really must consider light and its role when using telescopes. Up next, we have Jeff, and he will be explaining why small is not necessarily bad.
Hello, I'm Jeff, and I've been a member of the Mbo for 7 years or so. The telescope I use most is a 20cm Newtonian Reflector. It's reasonably transportable for dark sky viewing. It weighs about 7 kilos, yet it's too bulky to take on holidays. So I also have an 11cm Cassegrain Reflector. But I got to this point from an incident long ago and far away in my childhood, with a small telescope which lived in the bottom drawer of Dad's desk. Great-great-uncle Julius had brought it with him when he migrated from Germany to South Australia in the 1860s. We got it out occasionally, using it with great care, perhaps even reverence, to view the young moon or perhaps Jupiter. This refractor had a 32mm objective lens. Hardly worth it, some might say. When I was about 10 or 11, we lived in a small country town with few streetlights. It was essentially a dark sky sight, and on this particular night, Dad and I were out looking at the sky. He directed my gaze to the pointers, then to a star to the left, and then on to a very faint smudge. I learnt that this was the globular cluster Omega Centauri. We got out the telescope, and holding it up against the Hills hoist, I managed to train it onto that faint smudge. It was still a faint smudge, but a little bigger, fuzzy, and I was awestruck. Thanks in part to this ancient and seemingly inadequate telescope, I haven't been the same since. In time, I discovered that with my arm fully extended and my first 2 fingers spread, they pointed to Beta Centauri and Epsilon Centauri. And then, moving my arm further in the same direction, they pointed to Epsilon Centauri and Omega Centauri. Naturally, those instructions will change through the year with the apparent movement of the night sky, but it's an easy way to locate Omega Centauri. And it works equally for 9-year-olds or 90-year-olds, and anyone in between. Oh, and incidentally, well over 60 years later, I still occasionally take out that old telescope and view the night sky. But alas, where I live now, there is no Hills hoist.
Thanks, Jeff. Now I know that it's not necessarily the size of the telescope that matters, but how you use it is important. Stay tuned now for our final news break.
A SpaceX design for a new lunar lander vehicle has been selected by NASA to be used by the next astronauts to walk on the moon as part of Project Artemis. Beating out entries from Blue Origin and Dynetics, the human landing system will take the first woman and the next man to the moon by 2024 if all goes to plan. SpaceX were awarded $2.89 billion to make it happen.
Please keep your questions coming. Drop them into the comments and we'll attempt to answer them. Remember, there is a planisphere to give away for the question of the night. We now have Andrew showing us the ranges of telescopes available to us.
Good evening, all, and welcome to my presentation. By the end of the presentation, I hope you might have some ideas about what types of telescopes are available, which one suits your needs, and about how much it will cost you. Let's assume that you don't have ambitions to own your own radio telescope. Probably have trouble fitting it in the backyard. Or you don't want to launch a space telescope into orbit. It might just be a little bit too expensive. And you would like an optical telescope that enables you to directly observe or photograph the night sky. Oh, by the way, if you do actually want to work with a radio telescope, you can find out more about RAG, which is our radio astronomy group at Mount Burnett Observatory, and you can find that via our website. We'll start with the cheapest, simplest, and we'll work our way up. Refractors are the oldest types of telescopes, as Merv has demonstrated earlier, but also include binoculars, which are all you need for a surprising number of situations. They work with a system of convex lenses, which concentrate the light and magnify the image from distant objects by bending or refracting light. So here we see the objective lens converges the light rays, and then an eyepiece enables you to see the image either magnified or brighter. To observe the moon, some larger nebulae, star clusters, closer planets, and other objects needing a reasonably wide field of view, a decent pair of binoculars is all you need. For example, coming up in May on the 26th, there will be a total eclipse of the moon. This can be ideally observed through binoculars or a simple, inexpensive refracting telescope. You might need a tripod for easier viewing, it keeps it steady, or you can use a broom handle, or you can use a stick, just makes it easier to hold them steady. This one will set you back about $150, $140, and it's just fine for beginners who are not sure how enthusiastic they feel. This one, so spend a little. Or this one is nearly $2,500, and it's more of an accessory for someone who is very much committed to their hobby. It doesn't even come with a mount. The telescope at Greenwich in the UK is a refracting telescope with a 28-inch objective lens, and it's the 7th largest in the world. It was completed in 1893, mainly to be used for studying variable stars, and it's still used today. There can be problems with refracting telescopes this big. The glass lens is susceptible to distortion with variations in temperature, and even its own weight can have an effect. It can make it sag. Now, binoculars. With binoculars, they're really side-by-side refracting scopes. They work on the same principle. The two numbers describing their power tell you the magnification and the size of the objective or front lens. For example, 8 by 30 means an object will appear to be 8 times closer or 8 times magnified, and the binoculars have a 30mm objective lens. The wider the objective lens, the more light it can collect, as Stuart mentioned. So the higher the first number, the higher the magnification, and the higher the second number, the dimmer the object you'll be able to see. Now, there we go. Here's a fairly cheap set of binoculars, about $60. They have a 16 by 30, so you get quite a lot of magnification, but the objective lens is only 32mm across. If you want to lash out a bit, you can get a lovely big pair like this, which is 25 by 70, which means you get 25 times magnification, but the objective lens is 70mm across. So you get a lot more light then. So these would be okay for daylight, but these are a little bit more suitable for astronomy. Usually a telephoto lens is a refracting scope that attaches to your camera base. It is important that you also choose a suitable mount to get the maximum, get the maximum functionality for types of photos you may take. Neil has run several sessions with MBO members on astrophotography. A couple of things to note about refracting scopes. The higher the magnification, the narrower the field of view, usually, and the more will be the need for a solid mount like a tripod. The second thing to note, the larger objective lenses will enable you to see more astronomical objects like nebulae and globular clusters, but they're bigger and heavier. Neil will tell you all you need to know about telephoto lenses. Reflecting scopes. These are probably the best all-rounders for astronomical observations. They used curved mirrors to collect a wide beam of light and focus it to a point. There are two main types, Newtonian and Cassegrain. The Newtonian, you can see the incoming light is reflected by a parabolic mirror, which focuses it towards a flat secondary mirror, which then bends the light out to an eyepiece. You can see the front view here, which shows that that flat mirror doesn't take up much. There's still lots of light gets through. The trouble is, though, these have to be quite long. The Cassegrain doesn't need to be as long, so you can get a wider aperture without having to go to a very long tube. In this one, we get a parabolic primary mirror, which then is reflected again by a hyperbolic secondary mirror out through a hole in the primary mirror. So you can then put your eyepiece down here, as you can see on this illustration. And by the way, someone was asking about the images. The normal thing, for a Newtonian is that the image you see will be inverted. It'll be upside down. Cassegrain, I haven't looked a lot through Cassegrain. Somebody will answer that one, whether it's an inverted or upright image later. Our Mbo telescope is a Newtonian and Cassegrain in one. As you heard before, it's a 45 centimetre or 18-inch reflector in the base in our dome. And when we use it, most of the time we use it in Cassegrain, where the light comes down, hits the primary mirror, is reflected back to another curved mirror and back down through the base, and we view through an eyepiece at the base. But if we wanted to, when the light comes through the primary mirror, it can then go to a flat mirror up the top and out through this eyepiece up near the top end. I think you can see why we don't use it in that form most of the time. It's a little bit too far off the ground, but it can be either. This is a Newtonian reflector. It's an 8-inch reflector. These only cost about $700, brand new. It was first used for astronomy by its inventor, Isaac Newton, hence Newtonian. They're simple in construction and easy to operate. One like this is quite cheap, but you might even find it even cheaper online for less. You will pay more for a wider mirror and accessories like extra lenses or a prismatic finder, a finder scope, which allows you to look at 90 degrees. Now, this is very handy if the telescope is pointing straight up. You don't have to do calisthenics to get your eye to the eyepiece. You can also get a Telrad, which is a battery-powered device, attaches to the telescope. And when you look through this end here, you see two concentric red circles, which help you to line up with the object that you're seeking. It just makes it a lot easier. There are other types of Newtonian reflectors which can actually be separated into several pieces for easy transport, especially the bigger ones. Here's a Newtonian reflector that was made around 1795 and was used by William Herschel, who's famous for discovering Uranus. It's got a 7-foot focal length. The mirror is about 15 centimetres or 6 inches. You can see the sighting scope just up the top here. And you can just see the end of the eyepiece sticking out here. 1795 that was made. There's another telescope at the back you can see there. That's actually a refracting telescope that was built around 1774. Now, Cassegrain reflectors, they tend to be more expensive and more complicated, but they're much more compact and easier to transport. They often have motor-driven mounts and computer control, which allows them to follow an object across the sky, compensating for the Earth's rotation. This is much more convenient for the operator and facilitates longer exposures for more advanced astrophotography. However, with these features, they can take longer to set up if they are to operate effectively. This one is a Schmidt Cassegrain, which means it has a spherical rather than a parabolic mirror, and it has optics which produce clearer images. And this one also has an alt-azimuth mount, which we'll talk about shortly. Now, you can get a Cassegrain telescope for less than $100, but you get what you pay for. They range up to $10,000 or more if you want all the bells and whistles. A decent scope for astronomy will set you back about $1,000 or more. Again, you can probably find one cheaper, used online, but there's currently a lack of stock due to COVID, so you may have to shop around. This is probably the best telescope to buy if you want to take photographs, so make sure features include provision for a camera or video input for your computer. This one you can see here is a 90mm, so not a large aperture, but very easy to use. You can see manual controls on this with a couple of dials, and this has got an equatorial mount. You can lash out a bit more and get one like this, a 12-inch or 30cm Schmidt Cassegrain, which is near enough to $9,000. But you get, it's quite compact, and easy to transport, and it's got computer control, motor driven. The telescope in the Celestron Dome at Mount Burnett is a Schmidt Cassegrain. I believe it's a 12-inch as well. Now, this is the Gregorian reflecting telescope. It was made about 1755, and it has polished metal mirrors in the base here. So it is probably a Cassegrain type. Now, mounts are very important, and you really should be careful about selecting your telescope mount just as much as selecting your telescope. There are three common types of mount, and that's the Dobsonian, the alt-az or altitude azimuth, and the equatorial. The Dobsonian is where the telescope sits on a swivel base, and it allows 360 degrees horizontal motion and 90 degrees vertical motion. So this facilitates easy adjustment by hand and requires very little time for setup. The alt-az or alt-azimuth, which allows the same time of movement, 360 horizontal and 90 vertical, is your 360 horizontal base and your 90 vertical here. It has the same sort of movement as the Dobsonian, but it sits on a suitable stand or tripod and is often motor driven like this one. The equatorial is where the telescope mount is aligned with the Earth's axis. This axis here is parallel to the Earth's axis. The type of mount is most commonly associated with motor-driven scopes, but it also allows easy tracking of objects with manual scopes. This type of mount can be more easily used to find objects given their right ascension and declination. For many years, standard issue for Victorian state government secondary schools for science departments were 5-inch Newtonian telescopes with an equatorial mount. Our Monash scope at Mbo has an equatorial mount, and it's anchored 3 meters into the ground. This is where it's all going. These are the latest innovation for amateur astronomers. These models that you can see on screen are actually modified refracting telescopes with lenses, right, with primary lens. But and these are actually available from Vaonis, which I think are based in France, but they've got a website that you can see there. There is no eyepiece. The images are viewed on the screen of your phone or your tablet or some other device. You simply place your scope on a suitable surface, press the on button, and the scope will set itself up in a very short time using GPS technology. You then select the object you wish to view from the menu on the app, and the scope automatically finds it for you. By tracking the object across the sky and stacking images, the electronics of the scope allow you to see the object as closely and as clearly as you wish, depending on how long you want to take. You can then store the image on your device or send it to friends. Even light pollution can be filtered out. A rechargeable battery provides the power for several hours, so you can take it with you into the great outdoors, stored in your backpack. Another brand, the Unistellar EV scope, has an eyepiece, so-called, but it's actually a mini monitor. It's a modified Newtonian scope. Adam has more information about this fantastic development. You might say it's Adam and his EV. I hope this has given you some idea of what is available, and I look forward to your questions. Now, back to Petra.
Thank you, Andrew, for that educational information. I must say the smart telescopes have caught my eye. And finally, we have Adam talking about his EV telescope.
Folks, welcome to another night at the Observatory. I hope you're having a great night so far. You would have been seeing heaps of great talks tonight, and I'm going to be talking a little bit about smart scopes. Andrew was talking earlier and may have mentioned briefly and talked about the Vaonis Smart Telescope series, but I'm going to be fortunate enough to show you a smart scope in person tonight. We're going to be talking about the Unistellar EV scope. So it's a little bit different to other common traditional type telescopes in the fact that it's got a lot of computer equipment built into the telescope itself, and it's also got a really easy to use app and some software to make it really accessible for people with really sort of limited knowledge of the night sky and having access to some pretty basic equipment. So let's take a look at it now. Here is the Unistellar EV scope. So it's a really sleek, easy to set up piece of equipment. It's got a 2 kilo tripod, and the actual telescope itself is only 7 kilos. Really fast and simple to set up. It has an alt azimuth go-to style mount, so that means it's all electronic. It'll keep track of the night sky as you're doing your observations. So it's got a primary mirror in the base, and then it has a sensor up the top instead of a secondary mirror. So it's a Newtonian type reflector setup, but instead of having the secondary mirror, it's got the sensor. And that sensor gathers all the light and all the images that you're seeing, and it sends it to the eyepiece and maybe to a smartphone or a tablet display if you've got one. So really, really, really nice piece of kit. The app is really simple to use, so depending on what sort of objects you want to have a look at, you can go through the catalogue and it'll show you what's currently available above you. And unfortunately, we've got plenty of cloud over us tonight, but it doesn't really matter too much. If you've got really light cloud, it can still it's got the power to be able to see through that really light cloud. Really fantastic for urban skies as well. So we could take this into Melbourne with the night sky, with all the light pollution there. And because of the light gathering sensor, how powerful it is, it won't matter. It'll be able to cut through that and actually still produce a really nice image with detail and color like you've never seen. So you're probably wondering, okay, that's nice. What can I actually see with it? Well, like I said, the sensor, because it gathers so much light, is really, really good for deep sky objects. So things like nebulas, galaxies, and potentially even we've had a few people observing supernovas through them. So it's really fantastic. The other cool setup with this is that the app has the ability to do campaign citizen science observations. So observing things like asteroids, occultations, comet observations as well, and gathering really valuable scientific data. With lots of these scopes set up all over the Earth, we're basically making a big mirror over the Earth and observing the one object at the same time and gathering more information. So it's really fantastic. So it's really good for deep sky objects, not so great for the planets, unfortunately. So if you're really set on having a look at some of the planets and really bright objects in our solar system that are really close by, because the amount of light that the sun's reflecting off them, it's going to overpower the sensor, so it's not so great for that. So you're probably wondering, okay, Adam, what's the damage on one of these things? Well, they're about 2,400 Australian dollars, and you're going to have to get them from overseas, so shipping can take a little while, but it's all purchased through Unistellar. So that's pretty much sums it up. Like I said, it's a really fantastic, really easy to use piece of kit. Probably I feel has the advantage over other astrophotography setups where you need a lot of different pieces of equipment. With this, you can set up and start observing in about 10 minutes with really minimal effort, and pack up is an absolute cinch as well. So while they are a little bit more expensive, I think the benefits and the pros and sort of tend to outweigh the cost of it. So hopefully that gives you a little bit of an idea about the Unistellar EV scope. Thanks for watching. Enjoy the rest of your night. And if you've got any comments or questions, throw them down in the chat, and we'll get to them in the Q&A. That's all for now. I'll see you later.
Thanks, Adam. I do like your telescope. The future is looking bright with smart telescopes. That was our last of our speakers for this evening. Stick around for some brief notices before we head into our questions and answers.
Hello everyone. We hope you are enjoying the stream. Coming up next is the question and answer segment, but first, some important messages. Mbo is a volunteer-run organisation. If you'd like to support us, consider becoming a member, buying some Mbo merch, or making a donation. You can find us on social media at these addresses. The live streams are created by a talented and diverse team. You can read the names of those involved below. Now it's time for Q&A.
Okay, welcome back to our Q&A for the evening. And tonight's first question goes to Drew, and it's by Andy. Andy's asked, is the rotation of the sun parallel along the ecliptic plane of the solar system? Is that why all the planets are lined up on the ecliptic?
Okay, the first part of that is relatively easy. I believe the sun's at about 6 degrees to the plane, so it's slightly off. It's not quite perfectly lined up with the plane of the solar system. The second part of the question, and of course, the planets all have their own tilts that vary from fairly small to Uranus that's 90 degrees and basically spinning on its side. But the second part of the question is a little bit trickier. We believe that the planets basically formed from a disk of gas after the sun did, and that's why they're all lined up on the ecliptic. But the truth is, there are a number of theories on how the solar system formed, and we don't actually have perfectly down the science for it. So if you want to become astronomers and help nut out once and for all exactly how our solar system formed, go for it.
Great, thanks, Drew. I also have the next question for you as well. Dot has asked, curious, the Chinese use the lunar calendar and also has 12 animals in their astrology every few years. The 12th month also is doubled. Wonder if that relates to Ophiuchus. Never been able to work it out. And can someone tell her about the solar calendar versus the lunar calendar, please?
Okay, so the 12 versus 13, there are various numbers that pop up numerous times. In stories, you'll see the rule of 3, where a name has to be said 3 times for someone to magically appear, or Dorothy has to say, I want to go home 3 times, clipping her heels. In stories, 3 is a very magical number. In larger stories, in astronomy, all that sort of thing, 12 is one of those numbers. And so you'll see that appear quite often. It's just the way we tend to do things, along with the fact that 13 is a really awkward number to deal with. Being a prime number, it's not just odd, but there are no factors. You can't multiply things together, and it's really, really difficult to work with. So Ophiuchus basically just got the short straw and didn't fit in with the Babylonians. It wasn't the biggest or the smallest of the constellations along the ecliptic. It just was the one that they choose because they needed to knock one out, so it wasn't 13. So 12 is really a magical number as far as those sort of things go. Now, I could talk to you all night about solar calendar versus lunar calendar, but basically there were a whole bunch of lunar calendars, the Jewish calendar, for example, a lot of the Eastern ones that were all lunar-based and based around the moon, which is where lunar comes from, lunar, the moon. But the calendar we use these days is the Christian solar calendar. And that one evolved in numerous times through Julian calendar into the Gregorian calendar, and it's become the accepted one used these days. There is some slight problems with it. Easter is a classic lunar holiday, so it moves around in the solar calendar. And what we call a month, I've mentioned previously, came from moon. That being 28 to 31 days, it's jiggling it because the 28-day lunar cycle doesn't quite fit with the solar calendar. So we've adjusted to a solar calendar and smashed things to fit lunar-wise.
Great, thank you. The next 3 questions, I'm going to address them to you, Stuart. So we'll start off with Madeline's. With the telescope with the lagging orbit, how long till Earth catches it from the other side and what happens then? And Dimitra asks, have a question for you. You mentioned telescopes in orbit like Kepler have been decommissioned. How are they decommissioned? And Emma has also asked, what happens to outer space telescope satellites when they're decommissioned or stop working? I think you could answer all 3 of those.
Yeah, they're all about telescopes and satellites orbiting the Earth. Yeah. In the past, decommissioning telescopes wasn't the highest. Decommissioning anything going into space wasn't the highest priority. So there's a bunch of space junk floating around from old rockets that they shot up there when they were first learning how to. The Russians weren't too bad at that. The US was a bit worse at cluttering up space. But these days we're a bit more conscientious about all that, keeping space a bit more clean so we don't smash into things at high velocities. So yeah, the general trend these days is that low Earth orbit objects, satellites and telescopes that end their usefulness are allowed to slowly decrease their orbit or forcefully decrease their orbit so that they hit the atmosphere, slow down, and eventually enter the atmosphere and burn up in a beautiful a ball of fire. They usually do it over the ocean so that they're absolutely sure that it won't hit anything. But usually satellites just burn up in the atmosphere and become dispersed grains of microscopic dust before they hit anything. But further out, telescopes very far away from Earth, they often don't have enough fuel to get them to slow down enough so that they hit the Earth. They'll just end up in a small orbit or something. So for those, they usually like to put them in what's called graveyard orbits, which is just a fancy name for a really far away orbit that's by conventional wisdom far enough away that we don't have to worry about it for now. But space is very big. That's the advantage of space. So we can put a lot up there without worrying too much about it if it's very far away. And satellites that leave Earth's orbit, we don't really care too much about. We just let them fly off into space. It's very unlikely we'll encounter them again. That said, I was just looking up the Kepler telescope that's lagging behind the Earth, and yes, eventually it will come back around and meet the Earth in about 40 years or something, but I'm sure the scientists in control of that will keep a close eye on where that's coming and everything. It's very unlikely that it'll hit the Earth or get close enough to hit any other thing that's in orbit, because, like I said, space is very big, very spacious, you might say. Yeah, it's likely to get thrown away in some odd angle by the gravity of the Earth. But yeah, there'll be people keeping an eye on all that stuff.
Great, thanks, Stuart. The next question is for you, Andrew. Marlene has asked, I have a small dent on the cylinder of my NG telescope. Will that make a difference to viewing?
Well, yes, thanks for that question. Very good. It shouldn't make any difference at all if it's a small dent. I'll quickly show you with my telescope behind me, if you like. This, there you go. As you can see, it's mostly tube, and the mirror's down the bottom. Okay, so if you make a slight dent in here, you've still got all this width of light coming in. So the main thing that you've got to avoid getting dented or damaged is the mirror, of course. That's the thing that has to ice more than anything else. But the barrel itself, no, it wouldn't even matter if it had a few dents in it. As long as they're not too deep, it's not going to make any difference. I hope that answers your question.
Fabulous. Thank you, Andrew. Next, I'm going to ask you, Jamie. Annette has asked, what causes meteor showers?
Well, that's a great question. So a meteor shower is just a little remnants of comets and asteroids and things that are orbiting around the sun in the solar system as well. Now, that's those little dust particles, they hit the Earth's atmosphere at very high speeds and they burn up in the Earth's atmosphere, and that's where we get the meteor showers from. That is a very basic explanation of that. There is a lot more to it than that, but hopefully that answers your question.
Fabulous. Thank you, Jamie. Annette has also asked the next question, what would be a good beginner telescope for a teenager? And I think, Adam, you'd be great to answer this.
Yeah, thanks, Petra. Thanks, Annette. Great question. Andrew's talk earlier sort of covered this really well, but for a really low cost, really low budget, you could purchase a really good pair of binoculars as a great start to get to know the night sky. And then probably moving up from that, my suggestion would be a basic sort of Dobsonian telescope, like Andrew again just was showing his. They're purchased for a relatively decent price, and you can see deep sky objects, planets. You can change the lenses and try different configurations and really get to know the deep night sky with that. And then maybe if you're comfortable with that and you're feeling happy with that, you could move up to some more advanced equipment or potentially go into astrophotography if that's your interest as well. So there's lots of pathways, lots of avenues. The best way is to get started, and probably joining up as a member at MBO like myself and many others is probably a really good way to share that knowledge and do that. So I hope that answers your question.
Thank you, Adam. And I'm going to get Stuart to answer this next question. It's from Grinda. Doesn't the camera obstruct the light waves hitting the antenna?
Yeah, so you might have noticed on a lot of telescopes that they have a big dish at the back, and then the sensor that detects it is out in front of it. And even for amateur reflecting telescopes, if you look down the barrel, you'll usually find right in the middle of the telescope is this secondary mirror with a framework around it. Doesn't that get in the way? If I put a hand in front of the camera, you can't see me. But yeah, it's a bit different for a telescope. One way to think about it is that all of that stuff, all the camera and the frame, is all out of focus, so we can't see it. But yeah, it's a bit more complicated because there's light traveling in from all directions and everything, traveling in every direction. But yeah, if some light from one star is blocked by a section of the rigging or the camera, then there's another area in the telescope that allows that light through, and all the light from every star is traveling through all of the telescope. It's just it's better to think of it in terms of how much light it's blocking. And if you look at the whole telescope, there's enough light getting through that we can see what that light is. It's better to say it's all out of focus. But another point that's interesting to mention is if you've seen pictures of Hubble, all the stars have these points on them. Now, stars don't actually have points on them. They're all kind of spherical and blobby. Those sharp points come from the rigging. It's a lot more complicated to think about it because the light interacts in weird ways because it's a wave, and it's kind of ripples around the rigging and the secondary mirrors and everything. But that's what actually creates those star-like streaks coming away from points of light. It's the diffraction patterns of different arrangements of the structure. Yeah. But yeah, good question. It's a bit counterintuitive.
Fabulous. Thank you, Stuart. I think you've answered it very well. Okay, the next question is from Brett. Brett would like to know if there's a maximum size mirror from an optical telescope. Andrew, I think you're the right person to answer this.
I'll have a go. Yeah, it's not very. If you look back in history, they did attempt to make some very large mirrors, and the one that we were talking about the other night is Mount Palomar. The glass for the base of that mirror took something like 5 years to manufacture. So if you're just going to have a single mirror, it's very, very difficult to make anything bigger than 10 meters, for example, which I think was one of the biggest we've got now. But the cheats way of doing it is instead of having one big mirror, you have lots of smaller mirrors arranged in a parabolic or spherical or whatever array, and that will do just the same thing as if it was a single mirror, and focus them all to one point, and you've got yourself an even bigger one. So it's really, the limit is purely economic. Whatever you can afford, you can build it. Bigger the better. But of course, the problem is, the bigger it is, the harder it will be to move it. So that adds to the expense. But theoretically, you can make it as big as you want, as long as you can afford it. Okay.
Fabulous, thank you. Okay, we're just going to do a couple more questions, then I'll announce the winner for tonight. This next question is, what happens when viewing with stigmatism? I've always struggled with binoculars, microscopes, etc., but never knew why. Maybe it's because of my astigmatism. I'd love to know how to fix this and understand why. I think, Neil, you're probably the best one to answer this.
Yeah, I can have a go at that one. I'm actually someone who has astigmatism myself. So being an amateur astronomer and a photographer, my vision is very important. And so I am keenly aware of the limitations that astigmatism gives me. So long-sightedness and short-sightedness are caused by the shape of the cornea being too fat or too thin for what you're trying to do with the focusing. Astigmatism is a bit more complicated than that. It's a different shape of the cornea or the eyeball. So imagine that the cornea is squashed into sort of an egg shape, or the eyeball has been pinched or squashed into an egg shape. That means that rather than all of the light being focused at the same point, but a bit further back or a bit further forward, which is what short or long-sightedness is, the light is focused in not a single point, but in an area, and that happens at whatever distance you're looking. So short-sighted and long-sighted people can correct for that by putting on glasses, and they are able to have good vision in the other part. So if you're able to see, blurry at a distance, you can probably see fine up close without glasses. But people with astigmatism, they see the same level of blurriness throughout their entire range of vision. So we need glasses to correct for that. And the glasses are shaped to be very specific to correct for the view of each individual person's astigmatism, because it's different. Each person has it differently. It also is tricky in that its orientation is important, because the shape of the eye changes. It's not radially symmetrical. So I can't turn my glasses around and keep the images sharp the whole way through, whereas someone who's got short-sightedness or long-sightedness can. So how do we deal with this when we're looking through telescopes? Well, someone with short or long-sightedness, they can take off. Oh, sorry, my camera just decided to power down. 1 second. So someone with short-sightedness or long-sightedness, they can take off their glasses while looking through a telescope or a microscope and just simply change the focus, and that will correct for it. Whereas because of astigmatism, it doesn't matter how far away your focus is, you're still going to get some blurriness. You need to keep wearing your glasses. Now, that means that we've got this piece of plastic in our way, or glass in our way, and we can't put our eyes as close to the eyepiece as we might like to. So we need to find eyepieces that have a feature called eye relief, and that is the distance from the glass to where the light passes through the pupil. And you want an eye relief that is large enough that you can keep your glasses on while still getting the full view through the eyepiece. The alternative is to get surgery on your eye, which can be very effective. The problem with that, though, is that, at least in my case, my ophthalmologist has advised me that if I was to get surgery to correct my astigmatism, it would be 95% good enough. And because I'm so picky with my vision, that might not be good enough for me. Also, because I'm in my 40s now, as I get older, my eyes, or my lenses become stiffer, and so I have a harder time focusing closer. And when I'm looking at things like my computer screen or reading a book, I'll need to wear reading glasses. So I'll be probably ending up wearing glasses most of the time anyway. So I've chosen not to get surgery and to continue wearing glasses. And in my case, I don't do a lot of visual astronomy, so usually I don't have an issue with the eye relief. But if that's something you want to do a lot of, that's something you need to keep in mind when choosing the equipment that you're going to buy. I hope that answers your question.
Thank you, Neil. That was very informative. And now for our final question of the evening. And this one's going to go to you, Drew. Luke wants to know, why is it called the Ecliptic?
It's a great question, and one I'll answer fairly quickly. I mentioned that all the planets and their moons line up with the ecliptic, and the sun appears to move along the ecliptic. In particular, the sun and our moon both move around the Earth as far as we see, and we have, when the moon's in front of the sun, a solar eclipse, and when the moon and the sun are opposite, we have a lunar eclipse. So the ecliptic is named because that's the line in which the eclipses occur. So there you go.
Great. Thank you, Drew. Okay. We are now at the point we are going to announce the winner of the planisphere for tonight's question of the night. And the question of the night goes to Annette Peck, asking about what would be a good beginner telescope for a teenager. Annette, if you could please contact us on either our Mbo Facebook Messenger or on the email on the bottom of your screen there. That would be fantastic, and we will send out that prize to you as soon as we can. Okay, and on that note, the time has come to conclude tonight's show. Thank you all for joining us, and we all hope that you have enjoyed our first of many streams informing you about telescopes. If you have, please join us again for future shows, or you can rewatch any of our past segments on Facebook and YouTube. Don't forget to hit like or that subscribe button. If you have any further questions about telescopes, don't forget that you can join up as a member at any time at the website below, or come along to MBO. Good night. Take care. Until next time. Bye, everybody.